C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty. Good day, everyone. Hope you can see me okay. My name's Emma, and I'll be moderating today's session. So thank you so much for joining us. We're really glad to have you all online with us. And today's session is on exploring the thermal analysis of metal organic frameworks for carbon capture. So as the world moves towards a new green and sustainable future, we're leading the way in material characterization for some of these new novel applications. So today's webinar will be presented by my colleague, Dr. Genesis Infante, who's also our laboratory services manager here at C-Therm in our division of thermal analysis labs. And he'll be walking us through an in-depth and a really great overview of what metal organic frameworks are, what are they used for, and why characterizing them is important. So just a couple of housekeeping items before we get started. At the end of the session, we'll have a Q&A with Dr. Genesis, and I encourage you to save all your questions to the end so we can have a really engaging Q&A session. Don't feel like you need to use the raise your hand function on Zoom. There's a Q&A box at the bottom of your screen, and please put all of your questions in there and we'll be happy to answer them at the end. If there's any questions we don't get to today, we'll have someone from the C-Therm team following up with you directly to help you as best as we can. So without any further ado, I'll just do a couple introduction slides here before Genesis gets started. So just an overview of who we are here at C-Therm. So we are experts and leaders in the field of thermal conductivity, specifically the transient methods of thermal conductivity. So not the traditional steady state methods you might see, but the transient methods. And we have thousands of customers across the world in many different industries and in different universities across the globe. And over 50 distributors across the world. So whatever country you're in today, watching us from, whatever time zone you're in, we've got people on the ground to help you out, and you'll always be in good hands wherever you are. And if you aren't familiar or if you haven't heard of it before, our main instrument is the Trident thermal conductivity instrument. So there's 4 different methods available on the Trident platform. And it's a modular platform, so you can pick and play around with the different sensors that are available on the platform. Maybe you need an MTPS sensor, but not a THW. And the platform is modular in the way that you can pick and choose what you need for your application. So they're, like I said, all transient methods. You can get measurements in a matter of minutes with high accuracy and precision. And so this is kind of our bread and butter. This is what we're known for, is the Trident. And one quote we always kind of refer back to and kind of our guiding light is Abraham Maslow's famous quote, "When all you have is a hammer, everything looks like a nail." And this is perfect for the Trident platform. You may have a really great sensor, but it's not the right fit for the material you're trying to characterize. So some of our sensors are really well suited for liquids, whereas some of them are better for solids and thin films and powders. So they work on a wide range of materials, but you have to know which one to use in which setting. So that's why we offer such a diverse number of sensors, and so they can be used for different applications. And I'll get my colleague Angad to put in the chat here the link for a free download. This is our method selection guide in thermal conductivity. So we've provided an overview of many different thermal conductivity methods available, not only just the transient methods, but also the steady state methods. And we've outlined the pros and cons of each method. And it's kind of a tool that you can use and apply to your own application, so you can know which method should be used and which is best suited for your application. So that's a free download available on our website, and I encourage you to look into it if you're interested. And just a little bit more of a background on what we do here. So we not only sell and distribute our own instruments, but we're partnered with 2 other really amazing companies. So the first one is Rigaku Thermal Analysis. They're based out of Japan, and we distribute their line of thermal analysis equipment in North America. So the DSC, the STA, and the TMA, we've got all of those in our lab, but we also sell those if you're interested in thermal analysis. So they're really great tools. They're a really great partner, so we're happy to partner with them. The other one being Metrovib for their line of DMAs, dynamic mechanical analyzers. So these instruments have the highest force and frequency on the market. You can do completely automated testing 24/7 with the expander attachment. You can control it from your cell phone. So some really interesting offers here from Metrovib, and they're out of France. So again, a really fantastic partner. We love working with them, and we're very happy to be offering their line of DMAs. And finally, if you're not ready for that investment in an instrument right now, we totally understand, and that's why we have a fully equipped thermal analysis lab here at C-Therm, TAL. So we have all of those instruments that are distributed by our partners. We have a DMA, all of the equipment from Rigaku, the thermal analysis line, and some other methods, for measuring thermal conductivity, effusivity, not only our own methods being the transient methods, but also a couple steady state options as well. So if you're interested and you want to send us some samples to test for you, we'd be more than happy to. And we not only just send you back the data, but you can do a full kind of debrief with one of our subject matter experts to walk you through the data so you can really make sense of it and validate whatever results you're looking to validate. So if you're interested, please let us know. We'd be happy to help. And finally, before I pop off and give the floor to Genesis, I just want to share some feedback. We're always happy to hear from really happy customers. So here's a great testimonial we received from the National Research Council of Canada. Overall, they found the Trident to be reliable and user-friendly, and its performance has been efficient in delivering accurate and consistent results. So great feedback, and we're always really glad to receive that feedback from our customers. Alrighty, so before I ramble on any longer, I'm gonna hand the floor over to Genesis for the main bulk of today's webinar. So Genesis, the floor is yours. I'll stop sharing here, and I hope everyone enjoys today's session.
All righty. Thank you, Emma. So just sharing my screen right here, making sure everything's aligned. All right. So hello, everyone. Today, I'll be talking about the, thermal analysis techniques to be used for metal organic frameworks, specifically for carbon capture technology. So for those that are not familiar, metal organic framework, or MOF, which I'll be, just saying that a lot in this talk, are crystalline materials with select or a very specific porous structure that's self-assembled from building blocks, specifically a metal ion, or what we call nodes, and some sort of a organic linker. So in its simplest form, you can see right here, you'll have like a stick, for example, there's just a straight up linker. You'll have kind of this square cubic type structure where you have now a space in there where you can do, a lot of like reactions and whatever MOFs are able to do in general. So MOF have this, big advantage when it comes to applications in general, when it comes to like what's the purpose of these materials, right? So, compared to other macroporous materials, like inorganic type porous structures, MOFs has this unique ability to be very, very tunable. So, as you're creating your own personalized tunable MOF, you can like fine tune what kind of metal ion you'll be using, or depending on your application, whether you're targeting certain selectivity or certain chemical reactions, you can always modify your linkers and whatnot. So MOF has this really highly functional, highly fine-tuned, tunable types of applications where you can maximize efficiency with it. So speaking of applications, listed shown right here in the screen are just one of the few specific applications that the MOF can cover. There's a lot more out there. MOF is really this diverse group of molecules that are all over the place, has the potential to really, push forward the capabilities in general in terms of R&D and material science. But some of the few examples that I've shown right here is like gas separations and capture, energy storage, catalysis, drug delivery, and biosensing. But for the sense, for the purpose of this talk, we'll limit our topic into just the gas separation and capture, since we'll be targeting carbon capture and storage technology in general. But there's going to be some overlap on energy storage and catalysis maybe, but less of the drug delivery and biosensing applications. Okay, so carbon capture and storage. So Emma mentioned that earlier that we're modern times now, where everyone's aware that we have this global change on how we industrialize, and we're consuming a lot of things, and we're progressing in a development where everything has to be, we're generating a lot of waste, and one of those wastes is CO2 that and the greenhouse effects that really has a major implications in the global level. So there's a lot of movement in trying to mitigate CO2 in the air, and one of those techniques is capturing carbon and then somehow storing them in some way or form. So there's different ways that carbon capture can occur. One of them would be something like a post-combustion capture. So kind of directly capture the generated CO2 in a flue gas in a industrial setting, or a pre-combustion capture, so capturing the CO2 before combustion even occurs, and then a direct air capture, or removing CO2 directly from the atmosphere. So all of them seems to be similar in a way that you're capturing CO2 in one way or another. The only difference is that where or when you're capturing that in the process. But all of these steps have different implications on how hard or how effective they are. And then depending on the application, again, there's different things that you might want to take into account, whether, what kind of performance or what kind of form of materials you'll be using to be able to perform those applications. So, okay, so one of the adjacent to other than capturing the CO2 in general, MOFs can also be integrated into some sort of a membrane system, some sort of a filter system where you're separating entities or things from the air or liquid or gases in general. Or in this case, you'll have different materials right here where you have an input, and then going through this membrane where there's a MOF impregnated within it. And you can see that maybe it's selectively separating CO2 from all this mixture, and then maybe some of those gases also. So in this case, you're really filtering that and really increasing the effectiveness of the overall process, especially when the MOF is fine-tuned to have a very, very selective affinity to attract CO2 and prevent water or other gases from going through. So one of these results with this is that you can have really, really high efficiency and cost effectiveness on your overall CO2 capture and storage process. So once you've captured it, one good thing, like most approaches to store it in one way or another. Typically, you bury it down underneath the earth and kind of just forget about it. And one of the few approach is to actually convert the CO2 into something useful, mainly kind of like something chemical, like a fuel or like some sort of a plastic maybe. So that's where the MOF can start coming in, where the MOF can act as more of a catalyst in this case to help convert that into very useful chemicals at the end of the day. So all of that applications, all of that functions that I mentioned right now in terms of carbon capture and storage, it's really important to recognize that the key characteristics that really defines on how this MOF materials would behave or would function in general. There's very specific characteristics that needs to be met. So for that, we can define like, oh yeah, this MOF is very useful for this particular applications. So one of them, for specifically for CO2 capture, you'll want the MOF to have a high capacity. So you'll have a large volume maybe, or a large surface area where you can capture CO2 on the surface. And you'll need to have excellent kinetics to it, meaning the rate of this adsorption and desorption of these gases, that is relatively fast, so that you can have high throughput and cycling rate in general. And of course, selectivity is very important because air is a mixture of different things other than CO2. There's other things like oxygen, maybe, or nitrogen, even water. Water is very important to really make sure that it doesn't get inhibits the whole effectiveness of the MOF. And of course, you want to be sustainable in general, and you want your MOF to last not just like a couple use type scenarios where you capture CO2 and then you release it and then that's it, right? So you want it to be recyclable. And best case scenario, you want that recyclability to have at least 1,000 life cycle in general. And of course, you don't want to develop or have MOF materials that are not thermally stable, because we'll be showing down the road. Thermal management is a big part of managing or using MOF and all these different applications. And at the end of the day, even if you checked up all of this checklist with your MOF, if that particular MOF is not scalable in terms of, economically speaking, it's very hard to apply a really good MOF when it's really, really expensive to make, or very, very sensitive, or not, not chemically stable in general. Okay, so the main mechanism that we'll be looking at here is that you have a MOF structure with pores and volume that the gases can go through. And the main mechanism here is that you're capturing these gases through some sort of adsorption. So basically the gas will be on the surface, right? And then there's some sort of like chemical interaction right there. And and at some point you want that to be released, right? So all this process in a in an energy balance kind of way, when CO2 in general is being captured by MOF, and most MOF really, is that it is a exothermic phenomena. It's an exothermic process where when MOFs absorb CO2 or any gases where it's selected or designed to capture for, you have heat generation occurring. And vice versa, you need to it's an endothermic event when you want to release those gases from embedded on the MOF surface. So it's very, very critical to understand that this exothermicity of gas absorption process can really generate a significant amount of heat, and if not dissipated during the adsorption process, if it's not dissipated rapidly enough, you can raise the temperature of the whole system, which affects the effectiveness of the MOF on how to continuously absorb this gas. Because, like in a energy balance point of view, you don't want to input more energy during the absorption because you're just pushing it back to onto a reverse direction. So the issue now is that typically, ideally, the MOF has to dissipate this heat very effectively. But MOFs, being MOF, typically have a very low thermal transport properties. Mainly because there's different factors going through this, in which I'll be talking some of that. But part of the main reason is the form of it. Typically, it's in a powder form. It's highly porous, so you have essentially a lot of defects, and then there's going to be a lot of phonon scattering involved in that. So you basically have typically a low thermal conductivity and diffusivity property inherent into the property itself, which is not an advantage at all when it comes to gas adsorption or desorptions. So in terms of techniques used to characterize MOFs, there are many techniques out there that are standard effectively on when you have a MOF, like maybe the volume or the surface area and whatnot. We're not going to cover that in this particular webinar. What we're going to be focusing on would be more on the thermal management side of things. And one of those two techniques that I'll be covering would be something like a TGA DSC. So TGA, for those that doesn't know, it's a thermogravimetric analysis, and it basically monitors the mass loss, mass gain during some sort of a thermal ramp up or whichever condition you're exposing your material to. And DSC is the differential scanning calorimetry. It is basically monitoring thermal events, endothermic, exothermic, phase changes, glass transitions, and all of that when you're inputting heat into the system and see how your materials are reacting to it, right? So this techniques right here is what we also call as the STA, stands for the simultaneous thermal analysis technique. And in this particular example, the Rigaku STA Vesta is a TGA DSC instrument that can both do TGA and DSC simultaneously. And the other corner right here is our bread and butter for C-Therm, measuring thermal conductivity and effusivity, specifically the Trident's MTPS. What does the MTPS stands for? I'll be covering it in a bit. It's basically the modified transient plane source, but which all going to be relevant down the road. So first, covering the simultaneous thermal analysis method. So what can you really gain, or what can you get in terms of information from this technique related to MOFs and carbon captures in general? So as I mentioned earlier, we have the mass gain, mass loss. So you can just imagine if you have a MOF sample, you start absorbing gases or releasing gases, you'll see that you'll have a gain or loss in masses. Decomposition is very important. You want to understand the stability of your material. So mass gain, mass loss in combination with thermal event monitoring is very important in this particular application. Specific heat capacity, basically, the ability of the material to absorb, or the amount of heat that is needed to be absorbed by the material to gain a degree Celsius. Essentially, is very important for the thermal behavior of MOFs in general, which again has direct implications on its function when it comes to gas adsorption and desorption. And kind of like a unique in a sense for Rigaku is that there is also a sample observation aspect to it. So you can monitor any particular changes in your MOF during absorption, desorption, decomposition, or phase changes, but in real time, and it really gains a lot of the added insight into your studies of your materials. And of course, very basic standard thermal cycling. You can go up and down. You can have different temperature profile to it. So that's just part of the arsenal for the STA. And coming back to the thermal conductivity and effusivity, the MTPS, or modified transient plane source, it measures thermal conductivity, thermal effusivity. It measures all of this in a very rapid rate. In a scale of a few seconds, really, which basically you'll have a set of data by minutes, right? And compared to hours into traditional non-transient methods. More importantly, I think that is kind of resonates well with MOF in general is that it requires a very small sampling volume. So a lot of this MOF development, you'll have a small sample most of the time. And you can't provide kilos of it to do testing because it gets really expensive. So you really want to do testing under that small sampling size. Right. So a little bit of we're going to focus more on the thermal conductivity part of this talk. So this is just a close-up look of the MTPS. So you can see that there is that active region right there. Minimal size for volume that you'll be testing is somewhere less than 3 milliliters, really. So that could be a gram or two, depending on the density of your material. There's also options for pressurized cell. So this is how you would be doing testing when it comes to controlling the amount of atmosphere pressure, temperature, and vacuum maybe. So that is an option available for the MTPS. So diving into very specific examples on how the MTPS can give this information about MOFs and when it comes to its thermal properties, specifically conductivity, is that this example right here, published in 2017, you can see that they have their material on top of the sensor right here within this special container. And what they've figured out is that there is a direct correlation between pore sizes and essentially the thermal conductivity of the MOF material. So there's a trend where the pore structure and geometry really have that direct impact, and you can see that if you map out the correlation between thermal conductivity versus the cross-sectional area, you can see that it's very linear, and again, very strong indication of how that is. So which kind of makes sense if you really think about it. A larger pore size. So as you're increasing the pore size right here, you're decreasing the thermal conductivity as a whole, because now you have a larger void space, and then you're decreasing the density of your material, and which creates less pathway for phonons to transfer within the system. One thing to note though is that the biggest, again, well, I just want to reiterate this, is that the sample size is very important to note. That I think the author mentioned that they used maybe 1.5 mil altogether. And I think, again, another important note is that this is a non-destructive method, right? So you can always take back that sample and use that for any other testing. Another correlation from the same paper, again, here is that larger pore size typically correlates now that you'll have more gases contained within that volume, and then having more volume means that there is a large rate of collision between those gases within that pore, and that has a direct implication on how the overall thermal conductivity is now reflected. Meaning, you'll have higher rate of collision, and then that becomes essentially a source of essentially heat loss altogether within the system itself, which then again lowers the thermal conductivity of the material altogether. So if you go look at it the opposite, if you have a small pore size within that MOF, you'll still have gases within it, but then the collision rate within there is going to be a lot less compared to a larger volume, which then you don't see that in a significant effect on the thermal conductivity altogether. Another one that the paper really covers in this case is that the directionality of relative to the direction of the gas channel. There's one that's parallel to it, and then there's perpendicular to that direction. So when having more essentially gas going through, you can see that it is there's a lot more thermal conductivity measured, while in the perpendicular direction you see that there is a lot less. Right. So another paper right here specifically showcasing how CO2 loading can have a drastic effect on your thermal conductivity of the MOF, not just the structure itself. You can see that in the red line right here, these are pristine MOFs, so MOF 5 specifically. And at the really low temperature, what's trending here is that the loaded MOF with CO2 within it tends to have a low thermal conductivity, right? And then at higher temperature, you can see that it's becoming higher relative to just not empty MOF, right? So, this is basically, and again, as you go through this chart right here, the difference between the green, blue, and the purple is effectively the rate of gas diffusion within the system itself. So you're increasing the gas diffusion. You can see that all of a sudden, as you're increasing that with higher temperature, the conductivity is now trending in a more increasing path, right? So there is that correlation on not just the MOF structure itself, but the gases being involved, in this case CO2, and the rate and the amount of gases being involved in the temperature that you're measuring into. So going back to the thermal analysis, and more specifically the specific heat capacity of the system. So why should we care about specific heat capacity? Not just like the thermal events and how the thermal or the MOF behaves in general. There is a trend, right, or at least shown right here in this graph. You can see that there's a lot like different types of MOFs. The trend here is that specific heat capacity increases as a function of temperature. There's some thinks that there's a trend but these are not all MOFs. Some of them are carbon nanotubes. Some of them are actually zeolites and whatnot. In general, heat capacity is important for MOFs because a larger heat capacity means that the adsorbent, which is the MOF in this case, will have less decreased odds of undesired thermal effects because of the heat of adsorption, right? So when gases comes in and it creates all of this energy input into the system, and then you're releasing energy and whatnot. If the system itself can have a buffer and absorb that energy, you're less likely to have fluctuations in terms of your performance when it comes to gas adsorption, right? Another thing is that it's not just important in terms of function; it's also important on understanding how it behaves in general and how it trends, and then you can optimize it depending on how you do it in your R&D level, and basically just in your modifying your synthetic design as you go by trying to measure the trends and the thermal or heat capacity. So in this case, in this paper, what they've done is that they look into very specific MOFs, and they're trying to understand what dictates the thermal stability of the MOF in general, right? So we're looking at the thermal analysis now, and what they've seen is that there is a portion where you have a mass loss involved to it because of essentially removal of the solvent. There's kind of different MOFs right here. And at the end of the day, you can see that there is this T stability temperature here. It's essentially the maximum temperature where the MOF became stable after removal of the solvent. And you can see here that it's this lanthanum BTB is the top best performance versus something like a copper BTB right here, which has a thermal stability of only as 290 degrees C max. And you can see that in these TGA DSC graph. So you can see here in this graph, you have in green is the TG graph, and x-axis is the temperature point. So as you're heating up the system, you can see that there is associated mass loss. And then at some point, that mass loss stops, and then you'll have a stable region right here. And then you'll see a drastic decrease again at some point at about beyond 560 degrees C, basically, for this particular MOF. And the one in blue is essentially the DSC signal. And it's kind of a mess because it's very hard to really understand what exactly is going on here. But essentially, any peak occurring right here are associated thermal events. In this case, you can see here it's specified as exo in that direction. So they're all endothermic if we assume that the baseline is right here. And during that mass loss, you can see there's multiple endothermic events occurring. And then there's one major one, and then there's nothing for a while. and then another major thermal event, which is associated with the onset, basically degradation of the MOF. You can see the similar trend right here. You have some endothermic event and then nothing for a while, and then really just continuous degradation in general. And you can see that for these copper BTB, major difference between them is only the metal node, and then there's that significant difference on stability in general. So, when it comes to designing your MOF, you want to make sure that you're really maximizing, like maybe the coordination number or, the local environment around that metal node, because they'll have a significantly more direct implication on the overall stability of your material. And another example right here is essentially, a DSC with some TGA right here, but this is effectively a DSC signal. You can see that there's a bunch of different spectrum in there, different coloration. These coloration, if you follow from purple all the way to black, is essentially where they vary the CO2 to nitrogen ratio. So if you're coming from the purple, it's mostly nitrogen, not a lot of CO2, and then as you go by, it's just CO2. And you can see here that the MOF itself is behaving differently, meaning your thermal events are shifting as you're changing the amount of CO2 available for exposure. And for this particular MOF, there is a known structural change as CO2 being absorbed. So basically, as CO2 getting coordinated within the pore of the structure, that changes how the pore geometry of the MOF is shown, basically. So you can see that with a lot of CO2, you can see that really it changed the melting and crystallization events for this particular MOF. And you can also sort of like map that out with a correlation between the partial pressure versus the exothermic peak where it occurs, and you can see that there is that linear correlation, meaning they are directly related to one another. This just shows that just the DSC between different gas conditions. So it really tells you that the MOF doesn't really interact with nitrogen at all, so there's not a lot of thermal event going on there, but it does selectively absorb CO2 on the surface. This shows the loss on weight in general, mass loss, mass gain, depending on the gas. You can see again, no gain during the adsorption and desorption steps for nitrogen, but then there's the cycle between gain and loss of CO2 within the system. And I guess I'd say a very, very unique applications when it comes to MOF is when it comes to water, specifically water in the air, humidity, right? So water is, really everywhere, right? It's a ubiquitous component of the atmosphere, right? It's all around you, and unfortunately, it is a competitive adsorption against CO2. So most MOF will definitely encounter this issue. So a lot of the fine tuning is involved with making that hydrophobic in general, right? And on top of that, if you have water within your system, typically they chelate into the metal node, which has direct implications on how stable your nodes will be, and then overall stability of the MOF structure, which is very serious challenge, right? So studying how the MOF behaves under a controlled humidity is very important in this case. So for this example, on the right here, this is coming from Rigaku's STA with sample observation. So what you'll see here is directly on what happens on the MOF, on the crucible itself within the instrument. And you can see here, there's different graphs. There's temperature. You can see that they're not ramping up temperature, it's room temperature. There's a DTA, DSC signals, and then this is the thermal gravimetric signal. As you're adding the humidity, at this step right here, you can see that there is a increase on the mass. Again, it's pretty straightforward, meaning water is being absorbed. And then as you can see here, as the water is being absorbed, there is an exothermic event. There is a heat generated, and you can see that also the temperature increase right there. And then, as the humidity is being stabilized, it saturates the MOF. But then you can see here, this is really what you want to see is that how does the MOF behave once you want to release that water, right? In a passive way where you don't introduce any energy to the system, you can see that the rate of water loss is a lot slower than the water intake in this case. So, and then you can see here that at some point when water is actually coordinating within the MOF system, there's a color change from deep purple to this teal color. On the left, it's more about controlling the gas atmosphere that we are introducing to the system. You can see here that initially, no mass change, there's no change in the thermal events, no temperature change, and that's mostly because it's just helium being inputted to the system. It turns out helium is not coordinating within the MOF itself, so there's no mass gain introduced to it. And then once that helium is swapped to carbon dioxide, you can see that there's a drastic immediate response where you have a exothermic event and an increase in temperature and increase in mass right away at about 11% in this case. And then, and then saturates it. And then, remove the CO2, you can see that it immediately releases that pretty much very quickly once the helium is again reintroduced. So yeah, that's pretty much it for CO2 and then, thermal analysis techniques. For me, there's a quick summary right here, just to kind of like going over on the different points during the talk. You can see that thermal properties and behavior of the MOFs really determine on its function in general. The determination of how the thermal conductivity of the MOFs, we can do that using the MTPS, requiring very minimal sample volume and again non-destructive and in a very rapid testing time. Structure motifs such as like ligands, metal nodes, even the environmental conditions can really introduce a lot of variability on how the MOF's thermal stability and behavior can occur. And it's kind of like a double-edged sword because you can fine-tune it, but at the same time, you'll never really know what happens until you do your testing and making sure that it's robust against the conditions that you want to avoid or make sure that you want to target with. The DSC, the STA technique, basically the simultaneous thermal analysis technique. You can see how it was very useful when it comes to assessing thermal stability, behavior in general, and determining where that decomposition temperature happens, and then make sure that defining operational temperatures in general. So with that, that is my part for this webinar. I hope everyone gained some insights, and the floor is open for questions, basically.
Thank you, Genesis. I'm just going to do a very quick outro, just a couple slides, just to summarize the session here. All righty. So if you're interested in seeing any more of our webinars, we have tons of them on our website. So many different application areas. If this space wasn't specific to you, I'm sure your applications are probably covered somewhere on our website. So we have many different webinars from over the years that are available as free watches, free downloads. So feel free to check those out. And we also have a tech library full of publications, application notes, all sorts of different really valuable and rich documents. So if there's anything specific you're looking for, take a look there. And of course, if you can't find what you're looking for, we're more than happy to help if you just shoot us a message. A couple upcoming webinars that we've got planned out. So we're doing a an educational series over the next few weeks. So this is really great if you're new to the space of thermal conductivity and material characterization. And even if you're an expert in it, it's always good to learn new techniques and learn of new instruments on the market. So the first one coming up is the theory and applications of DSC, differential scanning calorimetry. So that's coming up next week on July 22nd. Following that one, we'll have a theory and applications session on just our Trident instrument. So the transient thermal conductivity techniques coming up on August 5th. And the last one that I'm sharing here is another theory and application session on DMA. So we'll feature our dynamic mechanical analyzer from Metrobib. And if you're interested in any of those instruments or techniques, please join us. Couple upcoming events that C-Therm will be attending. So at the moment, our CEO is at the battery show in Hong Kong. So we have a booth there with our partners from China. And if anyone's in that area, feel free to swing by. Following that one, next week on Thursday, we're hosting a free in-person event down in Texas. So it's an innovations day on many different material characterization techniques. There'll be presentations not only from C-Therm, but from different companies that are specializing in different areas of material characterization. So we'd love to have you there. It's free to attend, and we'll put a registration link in the chat. And then the next one at the beginning of August will be at the International Conference on Composite Materials in Baltimore. So we're at booth 608. If you're in that area, we would love to see you and answer any questions you may have, or if you just want to chat, we'll be there. This is the registration link here for the event we're hosting in Houston. I think my colleague Ange will put that in the chat. If you're in that area, we would love to see you there. It's going to be a really great session with lots of really great presentations. And finally, if you want to know more, you can always schedule a technical consultation with us. It's completely free. We'll hook you up with one of our subject matter experts to see a live instrument demonstration on any of the instruments you're interested in. And we can apply it to representative material. So if you're wanting to test foams, we can show you that. If you want to test thin films, we can show you that. Whatever you might be interested in. And like I said previously, if you're not ready to purchase an instrument, we do have a contract testing service where you can send us your samples and we'll do a full, data collection and then a debrief with you as well. So really great opportunity there as well. And if you know what you want and you're ready to place that request for a quote, that's completely free, free of charge, and we can get back to you super quickly with a quote for the Trident thermal conductivity instrument. We can help you, give you some guidance on the different sensors that might be more suited for your application. We've got a team standing by ready to help. So if you're interested, the link's in the chat, and we'd be more than happy to give you a quote. Finally, just to stay in touch or stay up to date with what we're doing here at C-Therm, the best place to see these updates is on LinkedIn. So we're always posting on LinkedIn all the different events we're at, the webinars we're hosting, all that good stuff. So give us a follow if you feel so inclined to. And with that, we'll do a little bit of a Q&A session here. So I'll stop sharing my screen again. I'm also going to stop the recording here.